Okay, in this topic, what we're going to be looking at are gradients and the directional derivative in a plane. And the idea is before we were talking about the derivative in the x direction, the partial derivative in the x direction, or the partial derivative in the y direction. But now we want to talk about the a directional derivative, which is the rate of change in some arbitrary direction. Before we get to that, though, let's just do a quick warm-up. What I'd like you to do is pause this video and find the partial derivative with respect to x and then with respect to y of the following function. And then unpause it, and I'll go through the solution. Okay, so partial derivative with respect to x, we're going to be using, in both cases, both product rule and chain rule. So if we take the first times the derivative of the second, well, that's derivative of e to something is just e to the x plus y times the derivative of that inside, which is just 1, plus now we take the derivative of the first, which is cosine xy, times the derivative of that inside, which is y, times e to the x plus y. And if we take the partial with respect to y, it's going to be very similar. We get the first times the second, or the derivative of the second, plus the derivative of the first times the second. So that tells us how this function is changing with respect to x and with respect to y. But what if we wanted to know how our function was changing in this direction? You know, if we were to walk in this direction, in the direction that is negative 4i plus j, if I were to walk in that direction, how quickly is my independent variable changing, my z value? Well, what we notice is that my z value goes up by 5. And how far did I travel to get there? Well, each one of these boxes is 20, so I went 1, 2, 3, 4 over. No, each box is 25. So I went over 100 and then up 25. So my change in the xz direction was square root of 100 squared plus 25 squared. So my rate of change then, the change in z over my change in both the xz direction, would be 5 over root 100 squared plus 25 squared. And that tells me how my z value changes in that direction. So here's a solution here. If we were to go through and evaluate it, that bottom was 103. So when we 5 divided by that, so it's a change of 0.05 degrees Celsius per meter. So our z value there was temperature. Okay, so let's develop this idea of directional derivative. So let's just imagine that we're at some point AB, and I'm going to move h units along this unit vector. So if I move h units along that new vector, my change in x is going to be h times ui, and my change in y is going to be h times u2. Because my change in position is going to be h times the direction, which equals hui, sorry, hui in the I direction, sorry, hu1 plus hu2 in the j direction. So here, 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 here. Okay, well that's my change in x and my change in y. Well, the coordinates of my new point then would be my original x value, a, plus hu1, comma, my original value, b, plus hu2. And so what I'm finding down here, this is just the change in z over the change in x, y. Notice that we have an h here because the amount that we moved was h. And this yellow highlighted, that's my new y value, f of my new point here. And then the green highlighted value is my original y value with my original point. So that's just a definition of slope, change in z over change in xy. Well, that should bring you to the idea of derivatives. Anytime you hear slope, slope, and derivatives, really the same idea, provided slope equals derivative, provided what's true? Well, provided that our movement, our h, is very close to 0. So notice that right here we have our slope equation, and when we let h equal 0, that gives us the derivative, the partial derivative with respect to our unit vector u at a and b. So that's the rate of change in the direction of the unit vector, and that's called our directional derivative. Well, just to really kind of hit this home, what happens if u1 equaled 1? Well, if u1 equaled 1, and u is a unit vector, the magnitude of u must equal 1. So if u1 equaled 1, then u2 would have to equal 0. So our unit vector would just be I. So in that case, if we go back to our equation here, we'd have the limit as h approaches 0 of f of a plus h u1, comma b, because now hu2, u2 is 0, so that's just b, minus f of a minus b all over h. And what is this? Well, since our b's aren't changing, in this case, this is just this equals the partial derivative with respect to x, because we're looking at changing just in the x direction. What's the point of thinking about that special case? The point of thinking about that special case is just to show that this is our general equation for directional derivative. And when we are talking about the directional derivative with respect to x and y, it falls into the same category of this equation, only either this term here or maybe this term would be 0. Okay, so a couple things that need to be true. U must be a unit vector. If U is not a unit vector, well, if U is not a unit vector, then it's not just giving direction. It would also it would change its magnitude.
So the purpose of u here, um, the purpose of u is it gives the direction in which we're interested in change. It gives direction without changing our magnitude. So the key thing, u must be a unit vector. So all it's supplying us is direction. Okay, let's look at a couple examples. It says for each of the functions f, g, and h, so f, g, and h, decide whether the directional derivative at the indicated points is positive, negative, or 0 in the direction of I plus 2j and 2i plus j. So if we look at the first case, I'm going to highlight the v's in yellow. Oops, that didn't work. Just to make it really clear, ideally more clear, there's my v, v, and v. So in the first case, the change of f in the v direction, we'll notice that it's following along that same contour line. So the z values aren't changing. So this equals 0. And what about in the next case? Well, in the next case, look at how g changes in the v direction. We notice that we were at 6. Our contour, we were at a 6 contour line, and now we're heading towards 5. So it's decreasing. So it's less than 0. And in the next case, our v, so the change in h in the v direction, we're going from 10 toward 9, also negative. What about my w's? Well, here we're at 4, we're heading towards 5, so that's greater than 0. In this one, we were at 6 and we're heading towards 7, also greater than 0. And in this last one, the change in h with respect to w, in the direction of w, we were at 10 heading towards 9, also less than 0. So the directional derivative lets us know how a function is changing, how the independent variable is changing in the direction, so the directional derivative, in the direction of some vector. What we would like to be able to answer is the following type of question. And we're going to have a hard way and then an easy way. So what we'd like to be able to answer is to calculate the directional derivative of this function at this point in the direction of the vector I plus j. So what we need to do is we need to get the directional vector into a unit vector. So let's call that u, and it's got a magnitude of root 2, so 1 over root 2i plus 1 over root 2j. That's my direction, and I'm going to go a little distance h. So when I go some little distance h, my change in x is going to be 1 over root 2 h, and my change in y is going to be 1 over root 2 h as well. So while my original point was 1 comma 0, my new point is going to be 1 plus, and let's write this in correct ways, root 2 over 2h. So the 1 coming from my original x, and that's my change in x. And my new value, well, I was at 0, and I'm adding root 2 over 2h. So therefore, my directional derivative in the u direction, so directional derivative in the u direction equals the limit as h approaches 0 of f of 1 plus h. Sorry, let me say that again. F of 1 plus root 2 over 2h, comma, root 2 over 2h minus f of 1, 0 all over h. So that's just looking at the change in z over my change in xy. All right. Well, if we evaluate that function, my z value for here, this will equal the limit as h approaches 0. So putting that yellow into my function, I have 1 plus root 2 over 2 squared plus root 2 over 2 squared. So that's the yellow evaluated minus now the point at 1 comma 0. So that's just minus 1 squared all over h. Oh, and this was h and h. Okay, so let's go forward and continue this kind of uh, tricky but manageable calculus problem. So if we expand this, we have h going to 0 of 1 plus 2 root 2h over 2 plus 2h squared over 4 plus 2h squared over 4 minus 1 all over h. Okay, well we've seen problems like these in early single variable calculus. What's going to happen are the h's, some h's are going to cancel out. Other things will happen. So the ones go away. When we do some simplifying, this equals the limit as h approaches 0. Well, in my first term here, you've got an h and an h, so you're going to, and a 2 and a 2. You're just left with root 2. And then we're going to have plus h over 2 plus h over 2. And as h goes to 0, this is just going to equal root 2. So that tells us how my function is changing in the I plus j direction. So in other words, we've got a slope of root 2. So we essentially a change of root 2 in the z direction with a change of 1 in the I plus j direction. That's what that directional derivative means. Well, that's tricky, and hopefully there's an easier way to solve that, and there in fact is an easier way to solve that, and we'll look at that right now. But here's a maybe cleaner solution to what we just did. But let's think about how we can find these directional derivatives potentially a different way. So to go through this proof, what we're saying is that the directional derivative in the u direction is given right here. And this numerator, well, that numerator is just our change in f. So our change in f is this right here. And we know that change in x is just our old x value minus our original x value. And our change in y is a plus hu2, sorry, b minus hu2 minus b. Because remember, we have the point AB, and we're having some change of h in the direction of u1i plus u2j. So my change in y is just hu2. So therefore, we can approximate using local linearity, which we learned in the last section. What we can do is we can say, well, our change in f, remember, is our partial derivative with respect to x times our change in x, plus the partial derivative with respect to y times our change in y. And we know that change in x is just hu1, and change in y whoops, sorry about that. And so our change in y here, hu2. And so what we see is that we can re-express change in f. We can re-express this change in f as the partial derivative with respect to x times hu1 plus the partial derivative with respect to y times hu2. Now if we do some substitution, so let's do some substitution and see what we get. Substituting above, we get that the partial derivative in the u direction at the point a comma b equals the limit as h approaches 0 of my change in f. Well, change in f is partial derivative with respect to x at the point ab, h times u1 plus partial derivative with respect to y at ab times h u2 all over h. And what cancels out? We'll notice that our h's cancel out. And therefore, we're left with an expression that has no h's in it. So as h goes to 0, well, that doesn't really matter. And we get the very nice equation that the partial derivative in the u direction at the point a comma b equals the partial derivative with respect to x at ab times u1 plus the partial derivative with respect to y at ab times u2. And this is a hugely helpful approximation which works using local linearity. So this is a hugely helpful approximation for us to quickly calculate directional derivatives using partial derivatives. Well, let's see how that works. So let's look at this kind of ugly problem that we did back here, and let's answer it nicely using what we now know. So given this new equation for directional derivatives, let's solve the same question. Well, we know that f partial x is 2x, f partial y is 2y. So at the point AB, or 1, 0, this equals 2, and this is equal to 0. Good. So we've found these two values. And now we need to convert this into a unit vector. Well, it's the same thing as before, root 2 over 2i plus root 2 over 2j. So therefore, my directional derivative in the u direction at the point 1 comma 0 is going to equal 2, and that's coming from here, times root 2 over 2, and that's coming from here, plus 0 from there, times root 2 over 2, and that's coming from here. So simplifying this, we get that this equals root 2. That's our directional derivative at that point in the direction of ij. And just going backwards, notice that we got to the exact same value before, only our new method is significantly more um, significantly quicker. Okay, so now what I would now what we're going to do is develop this idea of something called a gradient, and this is going to be a wonderfully useful um, math tool for us. So let's just suppose that there's some vector, and this vector is the partial derivative with respect to x at the point AB, and that's in the I direction, plus the partial derivative with respect to y at AB in the j direction. So this vector that we're describing is just how something is changing in the x, and we show that in the I direction, plus how the function is changing in the y direction, and that's depicted in the j direction. Well, what if we were to do a dot product of this new vector that we're thinking about? So if we dotted this vector with u1i plus u2j, so our direction vector. So if we dotted our derivative vector with our direction vector, what would we get? Well, using our understanding of the dot product, this is just f of x, or f sub x at AB times u1 plus partial derivative with respect to y at AB times u2. And that's just the definition of the dot product. Well, what is that? That should look familiar to us. This is the partial derivative in the u direction. Okay, well, therefore, this vector that we're just kind of creating clearly has some importance, because when we dot it, when we dot this vector with our directional vector, the resultant of that dot product is the directional derivative. So this vector is so important that we give it a name. And the name that we give it is the gradient vector. And gradient, think of like gradient in terms of, well, gradient is change. So this is our vector that's changing. And we call it, the shorthand we call it is grad f. So we say, well, I guess it's going to look grad f at a b. That's how you'd pronounce this piece. It's grad f at AB. And grad f at AB is, like we said, it's our partial derivative at x evaluated AB in the I direction, plus our partial derivative with respect to y at AB in the j direction. So the important takeaway from this, A, we're defining an important vector, the grad vector, the gradient vector, and that our directional derivative equals grad f dot u, where grad f is our gradient vector. So this is our gradient vector, and where u is our direction vector. So let's do one example, and then we're done. So it says find the gradient vector of f x comma y equals x plus ey at the point 1 comma 1. Okay. Sorry, I said we were going to be done shortly, but we have a couple more problems to go. I was getting ahead of myself. So anyway, let's find this gradient vector. Well, the gradient vector, we know, grad f at 1 comma 1 equals the partial derivative of f in the x direction, 1 comma 1, I, plus partial derivative with respect to y at 1 comma 1, j. Well, let's find these values. Partial derivative with respect to x is 1, and with y is e to the y. And if we evaluate both of these at the point 1, 1, this stays 1. This becomes e to the 1, which is just e. So therefore, our grad f at 1 comma 1 equals 1I plus ej. And remember, what our gradient vector is telling us is um, it's giving us a picture of the partial derivatives in their respective directions. So there's a couple just math language terms that we need to make sure that we're familiar with. The first one is this idea of this kind of, it's called del. And what del is, it's called the del operator. And what the del operator does is it takes the partial derivative of some function in the x direction and puts that in the I direction, and takes the partial derivative of function in the y and puts that in the j direction. So this is, if we were to take del, so if we say del f means we're going to take the partial derivative of f with respect to x, I, plus the partial derivative of f with respect to y, j. And this is exactly, this is our gradient vector, grad f. So there's just, there's two different ways in which we can, two different language methods. They're the same thing, but this idea of del f and grad f both mean the same thing. They both equal this. Okay, so what does the gradient tell us? So now we're going to get into some important geometric ideas. So let's think about what the gradient tells us. So first of all, what the gradient tells us, we know that the partial derivative in the u direction is grad f dot u. So if we use our geometric understanding of the dot product, that's the magnitude of grad f times the magnitude of our unit vector, which is just going to be 1 times cos theta. So it's just magnitude of grad f times cos theta. So when is the directional derivative maximized? It's going to be maximized when theta equals 0. And when theta equals 0, the biggest our directional derivative can be, so its max, equals the magnitude of grad f. So the magnitude of grad f is the biggest that our directional derivative can be. And it's in the direction of the of our directional or of our direction vector. Now that makes sense. So our grad f is our change, and this is our direction vector. So if we think about that, we've got some vector grad f or del f, and some unit vector, which is the direction that we're talking about that change in. So provided that these are in the same direction, that the angle between them is 0, that's going to maximize the change. When will the directional derivative be minimized? Well, it'll be the smallest when theta equals pi. Because when theta equals pi, cosine theta is the smallest it will be. So our directional derivative is a min, and the minimum our directional derivative can be is negative magnitude of grad f. And when will it be 0? It's 0 at pi over 2 or 3 pi over 2, because in that point, we're talking about how something is changing in the direction of u, where my change vector, my grad f or del f, is totally perpendicular. So if my change vector is perpendicular to my direction vector, then there's going to be no appreciable change. Now, just to make sure this doesn't get lost on you, uh, it's helpful to think about this in terms of physics. So let's just get to physics. Let's think about a ball that's thrown, and this ball is thrown with some velocity. Let's make it even better. This ball rolls off a table with some velocity, and the instant it rolls off the table, um, gravity starts pulling down. Well, this v, this is my direction, this little direction that I'm going in, and gravity, this del f, is gravity. And we know from physics that for that instantaneous moment when it comes off at a horizontal direction, that my gravity is pulling down, but it's moving in the x direction. So because these are perpendicular, the effect of gravity doesn't immediately affect its velocity. It soon will, but at the moment that it comes off, because they are in perpendicular directions, it is unaffected. Okay. So properties of the gradient vector that we just explored, thanks to the dot product and the geometric formula for the dot product, that the gradient vector points in the direction of the greatest rate of change. So the gradient vector is pointing in the greatest rate of change. Going back, we saw that our partial derivative in the u direction, so our directional derivative, was maximized when the angle between our u and grad f was 0. So this gradient vector is pointing in the direction of the greatest rate of change, and the magnitude of the gradient vector is the rate of that change. Okay. Let's just make that a little bit more clear, because if we think about del f or grad f, these values are fixed by the function. So by the function at some point a, b. So there will be some grad f vector. Our u vector can be, I could talk about the rate of change in that direction or that direction or that direction or that direction. So u varies. It depends on, where we want to talk about the directional derivative. However, when u falls in the direction of grad f, that's when it will be maximized. So therefore, if we force u to be in the direction of grad f, we will maximize our directional derivative. And so that's the idea of that. Our gradient vector points in the direction of the greatest rate of change. And so what would this look like on a contour line diagram? So let's think about that. Well, here we have a contour diagram, and imagine that I'm at the point A, B, and I want to go from this contour line C to my next contour line, some change in C. And what would be the fastest way for me to have that change? The shortest path would be the greatest rate of change. Because if we think about it, my green path and my red path my change in z is the same, but in the green path, on the green path, I didn't have to go as far to have an equal z change as I did along this red path. So therefore, if we think about what that implies, our, sorry, not our gradient vector, so our grad f, which is the same as del f, is perpendicular to the contour lines. Really think about what that means. The fact that it's perpendicular. So if I'm at this point, the fact that it's perpendicular means I'm getting away from that line as quickly as possible and getting to the next line. If I were not perpendicular, I'm sort of hugging that line for longer. So we want to have that change be right away. So creating that perpendicular line. So to summarize these, the geometric properties of a gradient vector in a plane, looking in a plane, are the following. The direction of the grad f is going to be perpendicular to the contour of f through the point, and it's in the direction of the maximum rate of change of increase of f. So it's in the direction of what maximizes our directional derivative. The magnitude of that gradient vector, grad f, is the maximum rate of change of f at that point. So that shows us how quickly our quickest rate of change can be at that point. And when the contours are close together, that value is very large because if it's close together, we're passing through a lot of z values quickly. Versus if the contour lines are far apart, we have to travel further to change a z value. So this is explain why the gradient vectors at point A and C have the direction and relative magnitudes that they do. Well, first of all, they've got the direction that they do because they're perpendicular to their contour lines. As far as the magnitudes, we notice that this magnitude from A is bigger than the magnitude from C. Why? Because going from point A, my contour lines were closer together, which means that as I move in that direction, my directional derivative is greater. I'm changing more. Versus at C, this contour line and that contour line are further apart. So I'm going to have less of a change. Okay, so this is the last problem. And so what we want to do is use the gradient, use grad f, to find the directional derivative of my function here at the point 1, 1 in the direction of the vector I plus 3j. Well, we know that del f or grad f at the point 1, 1 equals, well, we've already done this problem, but we can do it again. Well, partial derivative with respect to x is just 1, and the partial derivative with respect to y is e to the y evaluated at 1, so plus e to the j, or sorry, e j. So that's grad f. And if we dot grad f with the unit vector of this, so we need to change that into a unit vector. So that has a magnitude of root 10. So it's going to be 1 over root 10 I plus 3 over root 10 j. So to find the directional derivative, So we're looking for the directional derivative of f in the I plus 3j direction. This is going to equal grad f dot u. So when we multiply those components together, we're going to get 1 times 1 over root 10 plus e times 3 over root 10, which if we simplify, we get 1 plus 3e over root 10. And if we write that as in better math language, we have 1 plus 3e root 10 over 10. So that's telling me my directional derivative of my function x plus e to the y in the direction of the vector I plus 3j. So we're looking at the rate of change of a function in some random direction. This gives us all power in the derivative world. Congratulations for making it this far and for understanding this. We are done.